So let's look at case 3 here, where we're multiplying together a normal with a subnormal and getting a normal result. Now we're going to do this for the 4 cases of the most significant bits here. So we've got our 0, 0, 0, 1, our 1, 0 and our 1, 1. Now only a couple of these actually occur, so we only need to look at 2 of them. So let's first of all look at the case where we've got a 0 and a 1. Now an example of that would be 10,000 times 1.1 e to the minus 38. Now I've put those values into the calculator here and we've got the correct results. So let's first of all look at the exponent. Now the exponent is worked out as we would normally. The x value is a normal value, so we take this value here, which is 140, and that's the 140 down here. We subtract off the 127 to get the 13. Now in the y value is a subnormal value. So in the subnormal value, we always end up with a value of minus 126. So we've seen that in the previous videos. Now I just represent that as 1 minus 127. We add both these together, we get minus 113. We add on the 127 and we get a value of 14. So in this case as well, there's no bias here, so there's no shift. And you can see that here. This is the output that we get whenever we multiply together the mantisas. And you can see here that the decimal point is at this point here. And we can see that the actual result is going to be just a value 00100, and that's what we've got here, 00100. So we don't need to do anything with the biasing, because this number here is already normalized. It's a normal number and the leading value here is a 1. So it means that the final output is 14, and this is the binary value for 14, and that's what we've got at the output here. It's a normal number and this is a value 14, and we have the mantissa is the rest of the 23 bits here, which have been rounded, and that's what we've got here. So let's look at the second option. Now the second option is a 0 and a 0. The other options, a 1, 0 and a 1, 1, don't occur. So here's the second and final case that we're going to look at. And this is where we have a 0 and a 0 in these leading bits. Now an example of that would be 1e to the minus 39 times 100,000. And I've put those values in here and you can see the results. So let's again look at the exponent first of all. So we're going to have a normal times a subnormal will give us a normal result. So we treat these as we would normally. The xe is the normal number and it's going to be our 143, which is here. Minus 127 gives us 16. And the y value here is a subnormal value. So again it's going to be minus 126. So we add both them together, we get minus 110, and then we add on the 127 and we get a value of 17. Now that's not the end of it, because we're going to have a shift, or if you like a bias, in this particular example. And you can see that whenever we look at the value for the mantissa, and you see the mantissa, the full point stop is at this point here, and we've actually got a couple of zeros and we've got the 100. Now you can see up here we've got our 10011, which is the same numbers we have down here, but the position is different from the position here. So we can see that in order to normalize this value here, we're going to have to shift this 1 up to the first position here. So or equivalent, we can say we're going to have to take the decimal point here and shift it down. So we're going to have to shift it down 1, 2, 3 positions in order to ensure that the leading value is a value of 1. So we're going to have this value here of our minus 3 for the shift or the extra bias. So when we add these two together, we're going to get a value of 14, and the value of 14 is the value that we have here for the correct exponent. And you can see that what's going to be left over for the mantissa is going to be everything to the right of the new position for the decimal point, which is going to be 0, 0, 0, 0, 1, 0, 0. We've got that 0, 0, 0, 0, 1, 0, 0, and the rest of the values here. Now those are the only two we're going to look at, because the value 1, 0 and the value 1, 1 don't occur. So we have one more case to look at, which is going to be our normal times a subnormal, giving a subnormal result. And we'll get onto that in the next video. And when we've finished looking at all of these four cases, we'll get together all information that we've learned over these four videos, and this will help us to go ahead and design an efficient multiplier for our floating point numbers. So thank you for listening. I'll get you on the next video. Goodbye.